lecture 33, we're going to be looking at how the vector concept can be applied to model real-world phenomena. For example, we're going to be looking at different things like velocities and forces being acted on objects or as properties of objects, and then use what we know about vectors to answer the question mathematically. So let's look at a few examples. First of all, we got a ball that is thrown with an initial speed of 15 miles per hour in a direction that makes an angle of 15 degrees above the positive x-axis. What is the velocity vector v, and what is the initial velocity in the x direction or the horizontal direction and the initial velocity in the vertical direction? So we can break down the components of a vector into its horizontal and vertical components once you know what the vector actually is. And this is just a physical explanation of what we did at the end of lecture 32. We know that we have a vector that makes an angle of 15 degrees with the positive x-axis. We know that it is representing a velocity or a speed of 15 miles per hour. Note that speed is a magnitude, not a vector, but velocity, right, is a vector. So the magnitude of v is 15. So this length here is a length of 15, and we know its direction angle is 15 degrees, which means that v would be 15 times cosine of 15 degrees, right, where the 15 here comes from the speed and the 15 here comes from the direction angle, times I plus 15 cosine of 15 degrees times j. And when we're representing physical real-world phenomena, we're going to go ahead and approximate the solution using our calculator. Make sure your calculator is in degree mode. 15 times cosine of 15 degrees is 14.5. So that's the x component, plus, and this should read sine here, 15 times sine of 15 degrees is approximately 3.9j. Now our units is miles per hour, so what this says is that this is the velocity vector, and those units are in miles per hour, so the horizontal direction, the horizontal velocity, is 14.5 miles per hour, and the vertical velocity, or the vertical component of the velocity, would be 3.9 miles per hour. That's what those components then mean. In this example, we have that an aircraft is maintaining a constant airspeed of 500 miles per hour headed due south, but the jet stream is applying a velocity of 90 miles per hour in the northeasterly direction. We will assume then that the resulting vector is the sum of the two vectors acting on the plane. So first of all, the plane is heading due south with a magnitude of 500 miles per hour. But the jet stream is moving 80 miles per hour in a northeasterly direction. Without any more details provided, we're going to say northeast is going to be directly northeast, which means this makes a 45-degree angle with east, and it has a length of 80 miles per hour. So we can now, using this information, come up with two vectors that add together. Once we find their components, we can determine what is the resulting vector for the aircraft. What direction is it actually moving in? So first of all, part A, let's express the velocity of the aircraft relative to the air and the velocity VW of the jet stream, both in component form. Now, velocity of the aircraft is simple because it's heading due south. There is no x or x component to it. So v sub alpha, which is the aircraft, that's this vector here, is due south, so there is no x component and the y component would be minus 500j. Now, why is it minus? Well, if you think of this on a coordinate system, right, it's going down, so we're going to say negative 500 is the direction that that vector is going. It's going down instead of in the positive y direction. On the other hand, v sub w, which is the wind, what we know about it is if we drew the coordinate system here and put the origin at the base where that vector starts, we know it has a length of 80, and we know its direction is 45 degrees, which put those two pieces together, and what you have is this becomes the vector 80 cosine of 45 I plus 80 sine of 45 degrees j, which gives us 80, put this in a little bubble here, 80 square root of 2 over 2 times I plus 80 square root of 2 over 2 times j, or 40 square roots of 2i plus 40 square roots of 2j. So part B now asks us to do the following. It says find the velocity vg, that is a vector, of the aircraft relative to the ground. Note, and it tells us this, that the velocity of the aircraft relative to the ground would be the velocity of the aircraft relative to the air plus the velocity of the wind itself, which gives me a negative 500j plus a 40 square roots of 2i plus 40 square roots of 2j, which gives me, if I just take the I got 40 square roots of 2i plus, and in the j component, I got 40 square roots of 2 minus 500 all times j. Those are the values of the y components for the two vectors. So this represents then the position vector, or the velocity vector relative to the ground. Last of all, we're asked to find the actual speed. Remember, speed would be the magnitude of this vector. So then we're going to take, and in part C, we're going to squeeze this in here between these two lines. The magnitude of g would be the square root of 40 square roots of 2 squared plus 40 square roots of 2 minus 500 squared, which I'm just going to plug into my calculator and approximate, and I get relatively close to 447 miles per hour. Now, what direction does this aircraft actually travel in? Well, since we know, and maybe it helps to actually calculate these values, this is 56.6 I plus, actually it's minus, plugging this into my calculator here, I get negative 443.4j. So where is this vector? To figure out its direction, we're going to have to know where it's located. Since its x component is 50.6, which means it's positive, and its y component is negative 443, that vector is down here in quadrant 4. So my alpha, I can figure out this alpha right here, my direction angle, by doing tangent inverse of y over this x here. So negative 443.4 divided by 50.6. Plug that into my calculator. Tangent inverse of this value will give me this angle here, which we've referred to in the past as something like theta sub r for a reference angle, but that will give me this angle, the direction that it's flying, which is approximately 82.7 degrees, which means one way of describing the direction then would be in terms of how far away from due south are we. Well, if this is 82.7, then this angle inside here would be 90 minus 82.7, which is a 7.3 degrees. So that is you're going head due south, but then you turn 7.3 degrees to the east. We could write it that way. Now, you will be asked specifically in your homework which direction that these aircraft would travel. Depending on the language of the question, will determine how you answer that question. So if you have any questions, absolutely feel free to email your instructor as you're working on your homework. In the next example, we are given information about a piano that is being moved up a ramp at an incline of an angle of 20 degrees from the horizontal. We're told that two movers require a magnitude of force of 300 pounds to push the piano up this ramp. So in this case, we are going to use vectors to represent the forces that are involved. So I'm going to zoom in on this picture a little bit so you can see it a little bit better, because this is going to be where we represent the vectors. You have a triangle that can be formed by looking at this particular ramp. When you think of the piano moving along this ramp, it's moving in this direction, and you've got different forces acting on the piano. First of all, the piano has a force pulling it straight down, which that force, which is denoted by F1 here, is the gravity force. How much it weighs. All right. You also have a force acting along the ramp. That's this force that's being pushed here. You could think of it being applied here, because that's where the movers are going to be standing whenever they push on this. But that's the force right here that they're acting on. And remember that for a vector, location doesn't matter. So that's the same as if I move that vector down here and put it at the end. And the reason why that's helpful to put that there is that we know then, oh, didn't mean to jump around. Sorry about that. Let's go back to where I was. We know then that if you take these forces, the one going down and the one going across, then that there is the resultant force of those two acting together, which would be F3. All right, so F1 represents the force of gravity, F2 represents the force to move the piano, and F3 then represents the force of the piano against the ramp. Okay? Now, it turns out, just by looking at this picture, because of the direction everything's going, this angle in here will match this angle right here. That is also 20 degrees. So since we have a triangle here representing these three forces, we know the rules of trigonometry apply. So if I have this force coming down, this force going up, and this one's perpendicular to the ramp, then this is F1, F2, F3. This angle in here is 20. This is a triangle. Then we know that the sine of 20 degrees would be equal to the magnitude of F2, which is the opposite over the hypotenuse, which is the long side, F1. Now, why did I choose sine? Well, I know this value because they told it to me up here is 300. I also know the angle, and the question is, how much does the piano weigh? So we're trying to find the gravity. We want to know this one. So this equation right here, highlighted in yellow, is the trigonometric equation that relates those three sides together, the one I want to know, and two or three pieces that I want to relate together, where I know two of them, and then the last one is one I'm trying to find. Now all I got to do is solve that equation and I'll be able to find the gravity or the weight force on the piano. So this becomes sine of 20 equals the known force 300 divided by the weight. So the weight will be 300 over sine of 20. If I plug that into my calculator, it gives me approximately 877 pounds. And that's what you do. In this last example, we have a weight suspended from a bar with two cables. The box of supplies we know weighs 1,200 pounds, and it is suspended by two cables attached to the ceiling, as shown in this figure. The question is, what are the tensions in the two cables? Tension would represent how much force is acting in this direction and how much force is acting in this direction, when we know that there's a force down here acting down of 1,200 pounds. So the question is, how much of each of those forces are distributed across those cables? So in order to answer this, we need to understand what's called static equilibrium. An object is in static equilibrium, that's I-B-R-I-U-M, equilibrium, if one, it is at rest, and two, the sum of all forces acting on the object is 0. So this being at rest means we're going to assume that all the forces acting on that object is 0. So the sum of all the forces, in fact, if I called this F, let's call this F1 up here, let's call this F2, and let's call this F3, then F1 plus F2 plus F3 is equal to 0. Now, of these three forces, the only one I know completely is F3, right? F3 would be 0I minus 1200J. Now, why is that true? Well, because the only component is the Y component, and it's acting downward, so we're going to have a negative 1200J. Now, what about F1? What do we know about F1? Let's draw another picture here. F1 is acting in this direction here, and I actually have enough information to figure out what this angle right here would be for F1. We don't know how long it is, but we do know its angle, right? And how do we know its angle? We know its angle because this angle right here is 30 degrees. So this angle right here would have to be 180 minus 30, or 150. So its alpha is 150. So using the magnitude and direction formula for a component vector, we can write this as whatever the magnitude of F1 has to be, which we don't know yet, times cosine of 150 times I, plus whatever the magnitude of F1 is times the sine of 150 times J. We know that's the components of F1, we just don't know what its magnitude is yet. And similarly, we can do the same thing for F2, because F2 is going off in this direction, and we know for F2, this angle right here is 45. It's given right there in the picture. So for F2, we end up with magnitude of F2 times the cosine of 45 times I, plus the magnitude of F2 times the sine of 45, all times J. And this equation right here says all three of these had to add up to give me 0I plus 0J. So what that means then is we now have two equations. We have, if you add up all these things right here, they have to equal 0. And if you add up all these things right here, that has to equal 0. So how many unknowns do we have? The two things that we're looking for is we are looking for F1 and we are looking for the magnitude of F2. Those are the answers to that question right there. How many equations will I have? I have 2 equations and I have 2 unknowns, which means I have a nice little linear system that I can solve using what I learned back in algebra. Now, what do these equations actually look like? Let's get some space down here. You might have to squeeze this onto the any space you can find there in your notebook. Sorry for not giving enough space whenever I put this together. What does the equation look like? Let's fill it in. Okay, so I'm going to write this in blue. I've got 0 plus the magnitude of F1 from here, cosine of 150. Now, cosine of 150 is actually in our 30-degree family, so we know that that is negative square root of 3 over 2. And then plus F2 times, from right here, cosine of 45, which would be square root of 2 over 2. That has to equal 0. So that's my first equation. The second equation I have is from the second red block that I drew. I have negative 1200 plus the magnitude of F1 times the sine of 150, which is a positive 1/2, right, plus the magnitude of F2 times the sine of 45 from here, square root of 2 over 2 is equal to all 0. So there are my 2 equations. And I tell you what, just to make it easier to read, let's write this as the magnitude of F1 is my x and the magnitude of F2 is my y. This equation now looks like, just canceling out that 0, you have negative square root of 3 over 2x plus square root of 2 over 2y equals 0. And I'm going to move this 1200 to the other side. So this is 1/2 x plus square root of 3 over 2y equals 1200. So to solve this, I would recommend the easiest way to do that is to do a substitution approach. All right, let's use substitution. Meaning, let's take this equation right here and let's solve that for, say, y. Solve that for y and then plug that for y in this second equation. So this one right here would tell me that square root of 2 over 2y is equal to square root of 3 over 2x. And if I multiply both sides by 2 over the square root of 2, I get rid of it on this side, and I have y is equal to, 2's cancel, square root of 3 over square root of 2x. So now substitute that back in to this y right here. So you have 1/2 x plus square root of 3 over 2 times square root of 3 over square root of 2x equals 1200. So this, I gotta be careful. Oop, I made a small mistake. Catch it right here. This right here was a 2, so there should have been a 2 here. This is a 2 here. Sorry about that. So we caught the mistake. That's now square root of 2 over 2 times the y. The square root of 2's cancel, and I have 1/2 x plus square root of 3 over 2x equals 1200. So that's, if I take x out, I have 1 plus the square root of 3 over 2 equals 1200. So just multiply both sides by the reciprocal. X is 1200 times 2 over 1 plus the square root of 3. And I'm just going to plug that into a calculator and get an approximate value which is 878.5 pounds. Okay, that's the tension in the first rope. And to get y, I'll simply do this formula right here, which says I can take the square root of 3 over the square root of 2 times x, which is 878.5, or approximately 1,075.9 pounds. Okay, so let's just do a quick review. We've got the two tensions. That's what we were looking for. How did we do it? Walk through the process again. We assigned a vector to every force. We found their components here, here, and here. Once we found them in their component form, we added them up and set it equal to 0 because this system is in static equilibrium. By adding them together, we created two equations with two unknowns, and then we just solved the linear system using substitution, just like we did back in college algebra. So, not a short problem, but it shows you the power behind using vectors to model real-world phenomena.